All right, so this is also a problem that Professor Spelio did in class. First step, we're going to find the acceleration of a block M in terms of m, or little m, big M, and g. Little m being the mass of the small block, big M being the mass of the larger pulley. Okay, so we have a block with mass m hanging from a pulley with a larger mass m. It's released, and there's this rope that's wound up in the pulley. The pulley begins to unravel, and this block m falls by a distance delta y. Okay. We also have a no slip condition. What this no slip condition means is that this wound up rope is not slipping on the surface of the pulley. So when we have a no slip condition and we have rolling motion, which is what we have in this problem, we can start with one assumption. Um, so if I have an angular acceleration, so drawn as alpha, I know that I can have this relationship where I have a tangent acceleration, okay, and then an acceleration of the center point, ACM, which means the acceleration from the center of mass, and they'll be related to the angular acceleration by this equation. ACM equals AT equals R alpha, okay? So this is when I have rolling motion and no slip. So this is a general equation, okay? What that means that I can relate these quantities. But in this case, notice that for my acceleration for the center of mass, this isn't moving. This pulley is pinned, right? This center is going to stay exactly where it is, even though the object is rolling. So ACM will exist if my object rolls, right? Rolls forward, for example, like a ball rolling on a surface. But in this case, my ACM would be 0. That doesn't, this is a general expression that we can use. My AT will still exist, and it will still have this relationship to the angular acceleration, even though the object isn't moving forward. Okay, so that means that the tangent acceleration on this circle as it's spinning is actually going to be equal to this y acceleration as this object falls. So this is a general equation that's going to be important for us in this problem, that we can make the assumption that we can use right away because we have rolling motion with no slip. Okay. Also, we are given the mass moment of inertia, mr squared, and this is the mass moment of inertia for a disk that's rotating about the z-axis. So if this is like our xy plane, for example, the z-axis would be pointing straight up, so that means that it's rotating around this way. The mass moment of inertia is something that you can derive yourself. There's also a lookup table of many different mass moments of inertia. Some very common ones are on that table. This is a common mass moment of inertia for a disk. This is what we're going to be using for this problem. Okay, so to start out, we have this relationship and this relationship that we can use. And note that we can still use this relationship even if ACM doesn't exist. This is just telling us that if ACM did exist, we would be able to also model it with that relationship with R and alpha. Okay, so important concepts to start. Okay, so let's look at what the problem's asking. I'm going to do part A and pause and then post part B separately. So for part A, we're asked to find the acceleration of block M in terms of little m, large m, and g. Okay, so the way that we're going to do this is systematically, okay? I'll erase this for right now. We'll talk about that for part B later. Okay, so systematically, what I'm going to do is 1, I'm going to set up my free body diagram. 2, I'm going to do sum of forces. So sum of forces in the x, sum of forces in the y. And for our angular dynamics, we have one other thing happening, sum of torques. So if an object is spinning with, or if it has some kind of angular acceleration, we know that we have a torque force. In this case, we're going to write this as number 3, something that's important to know. The equation for torque, for just a single torque, is equal to R, okay, times the force acting times sine of theta. Okay, R is the distance the force is away from whatever the pivot point is, and then theta is the angle that the force makes between the distance in the pivot point and the force. Okay, so there's always some lever arm that the force is pulling on or pushing on that's a distance away from the rotation point. Okay. And just as we know that sum of force, okay, is equal to the mass times the acceleration, in this case, for our torque, the analogy for that is mass moment of inertia times alpha, which is angular acceleration. So the mass moment of inertia is the measure of an object's resistance to change in rotation direction, just as a mass can also be described as a measure of an object's resistance to change in linear acceleration. Okay, so we're going to set those up, and then third, what we're going to do is look at these other relationships that we lined out here. So we're going to look at equations 1 through 3 and see how that helps fill in any of the gaps that we might have left for our systems of equations. And then 4 is what's going to be algebra. Okay, so let's go ahead and get started. So number 1, our free body diagram. Okay, so 1, FBD. Okay, so anytime we have a mass, we can break it up and do a separate free body diagram for each mass. In this case, we have a circle, and we have this little square here. So note that this square mass can actually be modeled as a point mass. What that means is I can just draw it as a point with t coming up and mg going down. Okay, so both of these are equivalent and both of these are acceptable. Note that when I have angular acceleration, I actually need to model whatever object the torque is acting on as the full object, so I can note where the radius is or how the distance that my force is away from the rotation point. So I need the actual rotation point in my drawing. So for example, in this case, we have some radius r, right? And some of these forces are going to be acting around the radius. So I have a tension coming down from the pulley. I also have the weight of the pulley and then this normal force because it's pinned at the center. So the weight pulling down and then the normal force, like, so if this pulley was kind of, if this is like the pin through the pulley, it would kind of be touching that surface as the weight of that pulley is pulling down. These are not often modeled for pulleys. Sometimes you may see a lot of diagrams neglect the normal force and the weight, and they're modeled more like internal forces. In this case, they actually won't contribute to our equations at all, but we're just modeling them to show that they don't contribute to the overall torque. So let's see what I mean. Okay, we're going to look at block M. Oh, I'm going to model this little m. And then we're going to look at the pulley, large M. So we're going to do sum of forces in the x and sum of forces in the y, sum of forces in the x, sum of forces in the y, and then the last one for large M, we're going to look at the sum of torques. Okay. So sum of forces in the x. Let's look at this little mass M over here. Do we have anything acting in the x direction? No. So that would be 0, right? What about the y direction? So I just drew them in two different figures. They're just the same thing. So, okay, in this case, we have tension acting up, right? Tension minus mg, right? Because we're going to decide that this is our positive x and this is our positive y. Okay, so just a conventional coordinate system here. All right, then what is that equal to here? So we know that F equals ma. Okay, do we have any up or down motion here? Is this moving? Well, we are trying to find the acceleration that this block experiences when it's displaced. So we do actually have an acceleration. So it'll be the mass of just this particular object times the acceleration that it experiences. Okay, now let's look at the pulley. Do we have any sum of forces in the x direction here? No, all of those are going to be 0. What about sum of forces in the y? Okay, so we have n minus mg, right? And then we also have minus t, and that's going to be equal to 0 because this mass, right, is not moving up or down in the y direction or side to side in the x direction, right? It's just a stationary mass, okay? So we're going to set this expression, right, equal to 0. Okay, what about our sum of torques here? What's going on with that? Well, let me move actually this guy over and we can look at it a little bit further down. Okay, so sum of torques for, I have this circle for M just to show what the sum of forces equations are for. Okay, we're going to look at sum of torques just for this object. This object is not going to be spinning in our problem. This is the object that's spinning. Because the object is rotating, this is the one where we're going to check and see if it's experiencing a torque. Okay, so for the equation for torque, we know that R is equal to F times sine of theta. So if we look at each of these forces individually, we can see that N and MG are 180 degrees, so they're in line with the radius, right? They have, um, so the angle would be 0 or 180 degrees essentially. When a force is in line with a radius, it doesn't cause any torque. You could model that force as like R times N, right? R times N sine of 180 degrees or sine of 0. Um, Essentially, because this is 0, right, the whole thing is going to become 0. It also makes sense if you think about it. If I have, say, something pinned in the center and I'm trying to make it rotate, but I'm pressing on that center point, I'm not going to cause any rotation. I have to be a little bit of a distance away, right, for it to actually cause rotation, whether I'm at an angle at a distance away or acting at a 90-degree angle. I still need that to be able to cause rotation. Okay, so, all right, so I know that the torque for N and then the torque for my mg force, right, are both going to equal 0. What about the torque for my tension? Well, if I look at the distance, the angle that it has with the radial line, it has a 90-degree angle, right? So r is the distance away, so it has some radial distance away. It has some angle, 90 degrees. So let's plug those in, okay? So I have r times t sine of 90 degrees. Okay, now the important part here is this is just the general equation for torque. The important part here is that I need to ask myself, is this torque positive or negative that I found? Well, by convention, if the rotation for a torque is clockwise, it is going to be negative. If a rotation for a torque is counterclockwise, it is going to be positive. So let's look at our figure here. Well, the tension is pulling down. So if I imagine this is my lever arm, right, and I'm pushing with this, if this tension force is here, it's going to pull it around this way, right? So that is clockwise. That means that my torque is going to be negative. Okay, so now I have all of my sum of forces for my pulley, okay, for my pulley object and for this little mass. And the question is asking me to find this acceleration, okay? So that acceleration is going to be the acceleration in the y direction, right, of that pulley. So that's this variable here. And then I also have an equation here if I simplify this. So I know that my torque, what we talked about before, the sum of torques is equal to I alpha, similar to how the sum of forces is equal to mass times acceleration. So if I simplify this equation, I have negative r t is equal to I alpha, right? Okay, so what else do I have where I could put these equations together, right? I have t here, I have t here, I have some unknowns. How could I simplify things a little bit here? Let's see. In the beginning, we talked about when we have rolling motion with no slip, we can say that AT, which in this case, the tangent acceleration, right, coming off of this circle, is going to be equal to R alpha. So let's take that expression right there. So if AT is equal to R alpha. Okay, so we have this, right? That means that we can sub out the A that we're looking for our problem. So let's just do a change of variable so we can keep them the same. So we'll say A is equal to R alpha, the A that we want to find. Okay, that helps us. We still need to solve for everything in terms of the masses. Let's plug things in and see how far we get with that. Oh, let's grab one more thing too. We know that the I, right, is equal to 1/2 mr squared for a disk when it's rotating about its center. That's the mass moment of inertia, or the resistance to the change in rotation when you're spinning it about the center. The mass moment of inertia is going to be different for depending on where you're spinning an object, but there are common lookup tables for when you're spinning an object around its center. So let's label our equations here. I'm going to call this 1, I'm going to call this 2, I'm going to call this 3, and I'm going to call this 4. So I'm going to take equation 2, and then I'm going to sub in 3 and 4, okay? So I can get an equation for my acceleration. Then I'm going to use equation 1 over here, so I can have a second equation for my acceleration. So t minus mg equals ma. Okay, what about 2? So I have negative r t is equal to I alpha. Okay, so my I is equal to 1/2 mr squared, and I know that alpha is going to be equal to my acceleration that I'm trying to find divided by r. So let's sub that in. So times this acceleration divided by r. Okay, I also know that the radius that my torque is acting around is going to be the same as the radius for the mass moment of inertia, right? So this little r is equal to r because it's all just the radius of the circle for this problem. They're all the same. Okay, so we know this. Okay, so let's simplify some things here, right? So I have minus RT equals 1/2 mr times A. I notice that I can also cancel another r here. So I can cancel this r here. Then I end up with negative t is equal to 1/2 ma. Okay, that seems like something that I can use. Okay, what do I have going on here with my other equation that I started out with? So we start out with this guy and we sub some stuff in. Now, I think I'm almost done here. Let's add, I'm going to call this equation 5. Okay, let's add 1 plus 5. Okay, so what that's going to look like is I'm going to have t minus mg equals ma, and I'm going to add negative t, okay, equals 1/2 large M A. Okay, so these tensions will cancel, right? It'll be almost like I'm subtracting them, and I'm going to end up with a negative mg is equal to ma plus 1/2 ma. Okay, negative mg, and then I'm going to factor out my a, m plus 1/2 m, and then a is going to be equal to negative mg divided by m plus 1/2 times m. Okay, and I found my acceleration. Okay, so this acceleration is the downwards acceleration of this little block m, okay, as it's displaced, moving down, okay? And we found it because we know that this tangential acceleration when the object is spinning is going to be equal to this r alpha. So we were able to use our torque equation combined with one of our sum of forces equations to solve the problem.